Hello. Hello. I hope everybody can hear me. Bismillahirrahmanirrahim. I'm starting the meeting. Bismillahirrahmanirrahim. So, as you know, that system configuration is mentioned here on the slide. So this means what are the components of air conditioning duct system design? In air conditioning duct system design, these are the components mentioned here, which constitute AC duct system. That is number one, centrifugal fan blower, fan or blower, then main supply air duct. From the fan to the room, the main supply air duct is called main supply air duct. The next is main return air duct. On the suction side of the fan or blower is main return air duct. Then number four is branches of the supply air. Branch duct is that duct which from fan to main duct, which takes off and it is given to another room or another section of the building. Number five is branch of the return duct. Supply air ducts may be branched and return air duct may be branched. So this is also part of AC duct system design. Next point 6 is here. Duct fittings. What are duct fittings? In any duct system, there are elbows when we make 90-degree turn or 45-degree turn. Reducers when we reduce larger duct to smaller duct size, and enlargers when we need to increase duct size from smaller to bigger. Branch takeoffs, so we particularly T's or Y's, where we can take a branch from main duct. Branch entry, so branch branch entry where branch is made. So from the main duct, it takes off a branch at 45 or 90 degree, and T's. So branch entry, T's, and takeoffs, they're same thing. And next point 8 is air, then air 0.7. Let's go to 0.7. And 0.7 is system balancing devices. What is system balancing devices? It is butterfly valve, which can close fully or partially, air flow rate. Then multiple opposed blade dampers also can open or close fully or partially, flow rate of air. Then is 0.8. In 0.8 is shown air distribution devices. It is air distribution devices is actually they are supply air diffusers and supply air registers. The difference between supply air diffuser and register is diffusers have no control volume behind the outlets, and if the same diffuser had some control flow rate regulator behind it with a lever handle coming out of the opening, so that is called registers. Similarly, return air grills. Return air grills are simple louvers. They take return air from the room and bring it back to the suction line of the fan. Exhaust air grills are provided in the room where dirty, polluted air is taken off and it is compensated with fresh outdoor air. Now I'll discuss one of the two methods, two of the most important methods. There are three methods that I've mentioned earlier. Number one, velocity method. Number two, equal friction method. Number three, static regain method. So I'll discuss now velocity method of duct design. So first of all, we must select design velocities, and that I have given in previous notes. I've explained you there are certain velocities which are to be maintained in supply air main and return air main, and supply air branch and return air branch, depending on application, whether it is residential, whether it is commercial building, or it's office building, or amusement building like cinema, theater. So then we calculate pressure drops in each section and each run. What is a run? A run of a duct is length of the duct starting from fan supply point up to the point where it is to be discharged. So it may have straight duct, then it may have bends, it may have elbows, it may have teeth, and ultimately reaches to the room. This all length is called as run. So run, which is longest, which is the highest resistance, is called index run or critical run. So we select fan resistance, fan static pressure, depending on the system resistance, the longest run or critical run or index run. Now, we select fan against the highest pressure loss in a run. In a solid example in the book, it is 92 Pascal. It will come later on in this lecture. Now, balancing of damper is left open for the run in step 3 above. Now, balancing damper is left open. For main run or index run or critical run, no dampers are closed partially, so they are fully open. In order to show that this run shows the critical path. Then dampers in the other runs may be partially closed to provide pressure drop in all those runs at the desired flow rate. In the index run or critical run, pressure drop is maximum, and that is 92 Pascal. Fan is providing this pressure, but in shorter runs, pressure drop is less than 92. So because of less pressure drop in those runs, flow rate will increase. It will become out of control. So in order to stop unnecessary flow rate to shorter branches, which provide less resistance to the flow, it must be stopped with the help of dampers, partially closed. Then size of the duct for critical runs may be increased to reduce the pressure drop. Overall pressure drop in the fan for fan selection purposes depends on pressure drop in the critical run or index run. If critical run sizes are increased, pressure drop naturally will increase. So if space available, if building design is such that it is possible to increase the duct sizes, then it is better to increase the duct sizes in order to reduce the overall resistance. This will reduce the initial cost, running cost of the fan selection, fan electrical consumption. Alternately, the duct sizes in the other runs may be decreased to dissipate the excess pressure drop, while doing so keep velocity constant. So one more method, alternative method of balancing the pressure in the main run, that is index run, and the branches. The one method is to review the duct sizes of the branches, so is go to reduction of the size, and when you reduce the size of branches, the resistance will increase and it will become equal to the critical run. So in that case, you don't need temporal control of the air flow rate. So this will be well-balanced system without providing dampers.
Why?
Now, other method is equal friction method. These two methods, velocity method and equal friction methods, are mentioned in our textbook. And third method is not mentioned, which I'll talk later. Now, let's discuss now. This is most important method. I was practicing consultant in Middle East for 6 to 7 years in 1990s. But most of the method used in that country, Middle East countries, for Dubai, Qatar, and in Saudi Arabia, is this for engineers. The most favorite method. It is well-balanced method, most easiest method, and it takes much less time in designing. The most difficult method is static regen method, so which I will not discuss here. So let us take easiest and most commonly used method, which is called equal friction method. The first step is select the pressure drop gradient. This depends on experience, and my personal experience says that 4 to 5 pascals per meter in a small system, residential system, commercial system. Take just 4 or 5 Pascal per meter pressure gradient in the duct. This will remain constant. This pressure gradient will remain constant throughout the design for main ducts as well as branches. That is why this method is called as constant friction method, because we don't change this criteria of 4 Pascal, 5 Pascal per meter for all the ducts. It may be main, it may be branch, it may be supply, it may be return. So size of the duct against this pressure drop gradient and the required flow. How to size? This will be shown with the help of a graph. This is done with the help of the graph, and that graph is given here. It is given in your book, and it will come next. I'll show you how to use that graph. Now find equivalent length of each run. What is equivalent length? I mentioned that main straight duct length multiplied by delta P per unit length, it will be total friction loss in that straight duct. What about fittings? What about elbows? What about T's? What about junctions? What about reducers? For that we must go to the equivalent length method. So each elbow with size has a data table by professional engineering bodies, and that will give you per equivalent length of one elbow, one T of a particular size. That means that to your elbow pressure loss is given you what is the equivalent length. It is virtually, not really, virtually replaced with a straight duct. Every bend, every reducer, every fitting, every T can be converted into equivalent straight duct. So we add that straight duct length depending on that conversion table, and from there we calculate the whole equivalent length of the duct. Find the total pressure drop in each run. So in this method, in each run, we'll make tabulate that data, and first we draw sketch. From the sketch, we mark them A, B, C, D, every run and is calculated from the length of every run is calculated from that table. And then we select fan for maximum pressure drop among all. So what is critical run or index run? Pressure drop in that run multiplied by the volume flow rate will give you fan power. So on this basis we will select. Here is a skeleton diagram without scale drawn by me to clarify you. But actual diagram looks like this, which is very congested. So I cannot explain my things here. So separately, I have redrawn above with my own hand. But first see the actual diagram. This is the actual diagram. And it is in your book. And this is figure 6.2 of your book. So this is meant for duct material GI sheet, galvanized iron sheet, not for plastic, not for any other material. Duct may be made of plastic, duct may be made of glass fiber, duct may be made of wood, plywood, thing like that. But duct may be made of fabric, cloth. So this duct is for GI sheet. This type diagram is for GI sheet and for circular duct. Once you calculate circular duct dia, you convert it with the help of aspect ratio in rectangular duct or square duct. So air temperature should be taken as 20 degree and epsilon, which is absolute roughness I explained earlier, of the GI duct sheet is 0.00015 meter. That means 0.15 millimeter. So here you can see that volume flow rates are given on the left and right side, vertical axis, meter cube per second. Forward slanting lines are duct diameters, backward slanting lines are duct velocities. So let us come back to my diagram, this one, to explain you this diagram. So this I have drawn without scale to make it very clear for you to understand. So here is the diagram. You can see forward slanted lines are shown in red. These show the diameter in meter, 0.16 meter means 160 millimeter dia of round duct. 1.0 means 1.0 meter and 5.6 means 0.6 meter or 600 millimeter. So these forward slanted lines are not colored in actual diagram, they are black all. So for distinction, for clarity on the slide, I have colored it. Now this blue line, it is backward slanted line and they show the velocities 4, 6, 8, 10 meter per second. In actual diagram, they are black. Now vertical lines show on x-axis friction loss coefficient, friction loss gradient, which is 3, 4, 6, 10 pascals per meter. I have selected. Usually I select this range from 4 to 6. 5 is the ideal for my personal selection, personal design experience. 5 Pascal per meter friction loss gradient is the best for easy design. So this is how we design pressure drops in each run with the help of this diagram. Once we do this, now here's the diagram shown. This is a solved example in your book. By doing this example, you will understand clearly how equal friction method and constant velocity methods work. You can see this black line, this is fan, and this is main supply duct, this is main return duct. First we design supply duct. Similarly, the return duct, I have not shown branches. So similarly, return duct may have branches. So those branches are also taken into consideration. So let us go forward, supply line. So if we go, these ducts are branched. First branch is here, section B. Second branch is here after C. And third branch is here after D. And one more branch in the branch is there after G. So A, B, C, D, E, F, G, H, I. These are the sections of the ductwork which are marked for calculation purposes on the paper. So point 1, 2, 3, 4, 5. These are the outlet points. These are the rooms. These are the rooms, location of the room supply outlets. So, for example, first outlet, second outlet, third, fourth, fifth. For each outlet, we have already calculated cooling load. With the help of cooling load, we have already calculated volume flow rate of air to be provided here at point 1, 2, 3, 4, 5. So depending on these flow rates, we can calculate total flow rate of section A. Then section B will have actually that flow rate which is required at room 1. And section E will have that flow rate which is required in room 2. And section 3 will have that flow rate which is required in room number 3 according to cooling load. And similarly, section H will have volume flow rate of supply air at room number 4 according to its cooling load. And point 5, section I will have flow rate which is in room number 5. Now, by summing up, let us follow route A, C, G, H. It is highlighted as red broken line. Red broken line is highlighted for clarity on this slide. Now, for clarity, this run A, C, G, H, this is called run. So from fan up to the outlet 4, this is the longest run according to calculations. And here I have shown a cross for marking section G, this run. In section G, at a particular point, we must know what is delta, what is pressure drop gradient, Pascal per meter, what is diameter here, what is velocity here in meters per second, what is volume flow rate here. So we will mention on each section these things on the drawing, as well as we can tabulate it like this. For example, in your solid example, run AB has 28 Pascal drop, and run ACDE has 58 drop, ACDF has 43, ACGH has 92, ACGI has 82. In this table, 92 is the maximum. So we know that ACGH is the critical run or index run. Now we will take this as a maximum, and all other branches will be sized accordingly so that their pressure drop becomes equal to 92. Now we have to revise. You can see that in section AB, pressure drop is 28, while fan is providing 92. So all the air will pass through section AB because low pressure. It's the lowest pressure. In order to stop this overflow in one single duct, what we do is we provide damper here. So damper and partially close the damper to control the flow rate. This closing of damper will cause extra resistance to the flow, and its resistance will become 28 will increase to 92. So this is the way we balance the system. This is called balancing of the system by increasing the resistance of ducts, branch or section, and making it equal to the index run resistance. Now here is formula for fan power. Fan power is calculated with the help of this diagram to show that this is revision of this thermodynamics 1. In thermodynamics 1, I have taught you that steady flow energy equation. So applying a steady flow energy equation on this diagram, this is fan inlet, this is fan outlet, heat is 0. So this is adiabatic process, Q is equal to 0. Fan is supplied with work from the motor, so external work is done on the fan. So W in, energy in is equal to energy out. By applying energy in is equal to energy out, and assuming discharge velocity approximately 0, and assuming Z1 is equal to Z2. So here velocity head will be 0, and we can calculate fan power is equal to volume flow rate multiplied by delta P, pressure drop in the longest run. So in this diagram, the next point is how to balance the system resistance with the fan power. Now, once in this diagram, delta P versus pressure drop in the system versus volume flow rate is shown. So this blue curve shows fan. This blue curve shows fan curve. This is fan characteristic curve. Manufacturer tests the fan and provides this curve. This black curve is your curve, how your system works. System means duct work. How your duct work calculations are done and how it varies. How delta P in the system varies with flow rate. This curve shows where system or duct system curve cuts this red system fan characteristic curve that is shown down here, this green point. This is perfect match of your design condition. Design system was designed at state 1. Fan was selected accordingly and provide this design flow rate, volume flow rate of design. But after installation, after bad work of the contractor, after the bad workmanship of the contractor, after violation of the design sizes of the contractor, system may have this curve. System resistance may follow this curve. In this case, this fan will not go with this flow rate at this. If system fan will provide this flow rate, then its resistance will be higher than the system can. So that's why system will adjust itself and it will reduce the flow rate. So now Q actual will be less than Q design and system duct system will match with the fan characteristic curve. So this is how we check whether fan selected is suitable for the design flow rate and design flow conditions or not. So here is the formula for fan. This is integral VdP multiplied with mass flow rate from state 1 to 2. This we have learned in thermodynamics 1. And mv square by 2, this is the kinetic energy of the air leaving the fan. So fan has imparted to air this much energy. Static work, that is integral VdP, plus dynamic work, that is m dot v square by 2. This is energy. This is the outcome of this equation, the outcome of static fluid energy equation applied to fan, SFTE. From here, after calculation of this integral, volume flow rate in meter cube per second multiplied by P2 minus P1 plus m dot v square by 2. So this is the dynamic head. Now fan work is equal to, given by this equation 3 and 4, and actually this is equal to V dot P total. P total is the pressure drop, static as well as dynamic head of the fan. Now, this is not enough to select the fan. Fan can be selected with the help of hello, who is speaking? Please stop speaking. Anybody speaking? Please stop.
Kamran, please चुप कर जाओ.
Sir,
Please mute your mic. Please, everybody mute your mic. Everybody mute your mic so I could continue without disturbance. Now, fan efficiency, eta fan is equal to W fan ideal divided by W fan actual. Could you please mute your fan, please? All participants, please mute your fan.
UP9.
You are not muting your fan. You are violating my instructions. Very bad. You are not good boys. Now, fan efficiency is fan ideal divided by fan actual, W fan actual. W fan ideal is with the help of steady flow energy equation. W fan actual is given by the manufacturer or with the characteristic curve. Or this can be calculated with the help of efficiency. Manufacturers usually give fan efficiency curves. From there, your flow rate and pressure drop fan efficiency will be shown, and knowing the fan efficiency with the help of ideal fan work divided by fan efficiency will give you actual fan work. So fan is selected with the help of actual fan capacity, that is power. Here I shown there are three laws, there are three fan laws. Fan laws are followed, and that is, you see, if for constant density, if density of air remain constant, then by changing rotating speed or angular speed of the fan, so volume flow rate is directly proportional to angular rotation speed or velocity speed in RPM or RPS, rounds per second. So volume flow is directly proportional round per second of the fan, and under the condition density remains constant. That is why work is proportional to velocity square. So velocity square, that's why fan, so work is equal to any power is equal to delta P multiplied by V. So from here, since volume flow rate is proportional to omega and delta P is proportional to omega square, the product of V into delta P, we see that W fan is proportional to omega Q. So that means fan work increases by Q power, power 3 of the rotating is RPM. Now, second law, please mute your volume, mute your mics. Now, velocity remaining constant, volume flow rate remaining constant, and density is changing, that is temperature is changing. That case, delta P, that is pressure loss, will be proportional to density. So work will be proportional to density change. So higher the temperature, less the density and less the work. Lower the temperature, higher the density of air and higher the work required. So third law of fan is for condition pressure drop remaining constant, delta P constant and density changing. So volume flow rate is inversely proportional to density. Higher the density, less volume flow rate, and lower the density, higher volume rate. So omega is inversely proportional to under root rho, under root density. That's why fan work power is also proportional to reciprocal of 1 upon under root rho, in case pressure drop remains constant. These are the fan laws. Now, last requirement of ductwork design is, now you have calculated duct sizes, flow rates, power of the fan, selection of the fan, everything is done. Now what is remaining is noise control. So reduction of noise can be done at source. Fan, there may be disturbance, vibration in the fan. This vibration should be cut out by installing vibration isolators, rubber pads, springs, and inside the duct by putting lining inside the duct next to the fan and before the fan, at least 3 to 4 meters distance, any 9 to 12 feet length, not the whole length of the duct. And then diffusers. Diffuser selection should be set that it should not vibrate, it should not create sound. Velocity at the exit of the diffuser will be so low that it should not vibrate the diffuser vanes. So diffuser noise is very, very disturbing for occupants. Now, prevention of noise transmission through ducts, pipes, structural members, vibration isolators are used, springs are used, rubber pads are used, hangers are used with isolation pads, and inertia blocks are used for concrete. Equipment foundations are designed such that it should not transmit vibration to the floor, and sound attenuators in the duct are used, so it should absorb the sound of the fan and air flow itself inside the duct. Acoustic lining, it is called acoustic lining of the duct. Now, absorption of the noise is possible by increasing the absorptivity of the wall and ceiling. In the building where we are living, this is architect's job to design the building inside lining of the room where less noise is required, quietness is required, like auditorium or classroom, lining or cinema house, theater. Lining, walls are lined with absorbing, sound absorbing materials like thermocore and things like this, or gypsum, and that act as a sound absorber, sound attenuator. And that is it with my lecture. Thank you very much. So see you in the next lecture, inshallah, tomorrow.